The Aldol reaction is an important reaction in organic synthesis because it allows the reaction of an enolate with an aldehyde or a ketone to give initially beta hydroxy carbonyl compound, which can undergo elimination reaction to give the corresponding alpha beta unsaturated carbonyl compound. Classically or traditionally speaking, the Aldol reaction involves acetaldehyde. So let's take acetaldehyde and then we try to react it with catalytic amount of a base. So this is the structure of acetaldehyde. Obviously, acetaldehyde with an alpha position is actually acidic at that position. So that's the alpha carbon of acetaldehyde. Of course, just like other carbonyl compounds which have an alpha hydrogen at the or a hydrogen at the alpha position, they are acidic at that position. That's because the alpha carbon ion can undergo resonance to give the corresponding enolate. Now, if acetaldehyde is reacted with catalytic amount of a base, such as an alkoxide, such as sodium ethoxide, so if this is reacted with sodium ethoxide catalytic amount, then the corresponding enolate is actually formed. Somebody may not think of an alkoxide as a suitable base to deprotonate carbonyl compounds at the alpha position. That's because of the base strength. Of course, carbonyl compounds are acidic, and the pKa, let's say in aldehydes, for example, is about 17 or 18. For ketones, it's about 20 at the alpha position. For esters at the same position, it's about 25. So typically, you would not think of an alkoxide in order to do the deprotonation chemistry. That's because of the base strength. Of course, alkoxides are conjugate bases of alcohols whose pK is about 16. So the alkoxides in general are not suitable enough, or they are not capable enough as bases to deprotonate carbonyl compounds at the alpha position. Typically, you would think of amides such as LDA, for example, to convert a carbonyl compound with an alpha hydrogen or a hydrogen at the alpha position completely into the corresponding enolate. But in this case, if an aldehyde like acetaldehyde is treated with catalytic base such as sodium ethoxide, catalytic means, of course, less than the stoichiometric amount used of acetaldehyde. So if there is 1 mole of acetaldehyde and, for example, 0.01 mole of an ethoxide, so that 0.01 mole of the ethoxide ion should convert 0.01 mole of acetaldehyde to the corresponding enolate. And of course, the amount of the enolate would then be 0.01 mole of the enolates. Let's draw the structure of the enolate, and then we can take it from there on. So this is the enolate, and of course, again, that's the alpha carbon. If there is 0.01 mole of the enolate as a result of the initial deprotonation reaction of 0.01 mole of ethoxide with acetaldehyde, then that enolate, 0.01 mole of the enolate, should react with 0.01 mole of acetaldehyde unreacted, because there should be 0.99 mole left unreacted. So the enolate would then react with the same amount of acetaldehyde unreacted, and of course that reaction or this reaction type is very characteristic. It's actually called nucleophilic addition, when a nucleophile attacks an aldehyde or a ketone, a typical reaction type, of course, of aldehydes and ketones. Aldehydes and ketones undergo nucleophilic addition reaction. The nucleophile in this case is, of course, the enolate. So this is the enolate. The product that's obtained is beta alkoxy aldehyde. So this is the alpha position, and of course that would then be the beta position. It's beta alkoxy carbonyl compound, beta alkoxy aldehyde. And of course, when the ethoxide deprotonates, we can show that actually. So this is the ethoxide ion. When the ethoxide ion deprotonates, it takes off that hydrogen to make the corresponding enolate, so that's the enolate. And of course, at this stage, when the beta-alkoxy-carbonyl compound is formed, there's no ethoxide left. There's actually ethanol. And again, the same amount of it, 0.01 mole of ethanol. Now, this ethanol unit or ethanol molecule should act as a proton source to protonate that alkoxide, if you like it. So the alkoxide would then pick up a proton from ethanol to give beta hydroxycarbonyl compound. So this is beta hydroxycarbonyl compound along with the ethoxide ion regenerated. So there's ETO minus, or the ethoxide ion, reformed. And of course, the same amount of it, 0.01 mole, for example, or whatever, 0.01 mole of the ethoxide ion, which can be used to do another deprotonation to give the another 0.01 mole of the enolate, which can then undergo another nucleophilic addition, and so on and so forth until the aldehyde, the original starting material, if you like, or carbonyl compound, is fully consumed. This beta hydroxycarbonyl compound is the initial product, but as we will see shortly, this beta hydroxycarbonyl compound can undergo elimination, and it will, and it does undergo elimination reaction to give the corresponding alpha beta unsaturated carbonyl compound. Now, this is a classical Aldol reaction. It's called Aldol because the product contains an aldehyde and an alcohol. If you look at the structure of the beta hydroxyaldehyde, this is an aldehyde. It contains an aldehyde functional group and thus ald. So the ALD in the Aldol reaction, and the Aldol name comes from the aldehyde functionality or functional group. It's called also aldol, so there is ol. So the ol also comes from or stems from the fact that the product contains an alcohol function group or a hydroxyl function group. So the product is actually an aldehyde and an alcohol, and that's exactly why it's called aldol. So the aldol reactions typically is an alpha condensation reaction of acetaldehyde upon treatment with catalytic amount of a base. An enolate is formed, and the enolate undergoes nucleophilic addition reaction to give initially beta alkoxy aldehyde, which can undergo protonation with ethanol that's formed to give beta hydroxy carbonyl compound, beta hydroxyaldehyde, of course, with release of the catalytic amount of the base. So this is the Aldol reaction in summary. It's a reaction between an enolate and an aldehyde or a ketone to give beta hydroxycarbonyl compound.